Welcome back to Honors Calculus. I apologize. I hate being a disembodied voice, but apparently today my camera has decided not to behave. In this video, we will be starting into lesson 9 on differentials and differential form of the derivative. But before we can get there, we need the background idea of implicit differentiation. The idea here is to look at an equation that does not appear to define y as a function of x. For example, something like y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Does not feel like y is a function of x. But we still might want to answer the same questions we answered for functions and graphs of functions. Namely, can we find the equation of the line tangent to this curve at a particular point? And we're going to do that by assuming that y is some function of x. Then, if we take the derivative of both sides of this equation, we can use the linear property of the derivative to split this up and separately take the derivative of y cubed and of y squared of 5y x squared and then on the right hand side we might as well note the derivative of 0 is 0. Now in each of these expressions we have y as a function of x. So when we take the derivative with respect to x, we are going to need the chain rule. The derivative of something cubed is 3 times that thing squared. And then the derivative of y is y prime. Likewise, the derivative of something squared is 2 times that thing. And then using the chain rule, we multiply by the derivative of y, which is still y prime. The derivative of y is y prime. And then we get to something that just has x's. The derivative of x squared with respect to x, we are taking the derivative of something based on x with respect to x. This time we don't have to worry about anything weird with the chain rule. This is just 2x. The derivative of a constant is 0, giving us this equation. In order to clean things up a little bit, we can notice that these three terms have a y prime in it. These are 0, they don't even matter at all. This one does not have a y prime in it, so let's move that over. And let's also factor out the y prime from the three terms that have it. So we have 3y squared, we have 2y, and we have minus 5, all being multiplied by y prime, and then that's equal to 2x. And to get y prime by itself, we divide by that nasty mess, and we get that y prime is 2x over 3y squared plus 2y minus 5. And so we've now been able to find the derivative of a function when it didn't feel like we had a function in the first place. It's a little bit strange having a derivative of y that also has y sitting in it, but that's the price we have to pay. Right? We're not sure that this curve actually defined a function, and in fact, it did not. There are places where this curve is not well defined. Well, sorry, not that it's not well defined, it's not defined as a function. There's particular values of x which have more than one corresponding y value. So to evaluate the rate of change, we need to know where we are in the curve, not just in terms of x, but also in terms of y. Let's take a look at another equation before we get into how we want to use this. This time, let's take a look at an equation of an ellipse. Something like x squared over 25 plus y squared over 9 is equal to 1. Right. This is, as I said, an ellipse. If you've studied analytic geometry and the conic sections, then you can quickly identify that this is going to be an ellipse centered at the origin, and it's going to have extents of 5 in the x direction, extents of 3 in the y direction, and produce a curve that looks kind of something like that. If you've not studied ellipses before, don't worry about it. Graphing an ellipse is not a necessary skill here, but this is a nice equation to work with because we can graph it and talk about it. We have set fixed x and y values on this thing, which makes it so that we can a little bit more carefully define what's going to happen as we work through it. Once again, to find the equation of a tangent line, we have to start by finding a point. And as we saw in the last example, points don't give us just a particular value if we know x. We need to know a combination of x and y. Let's say, for the sake of argument, that this point is 5/3 2 square root of 2. Before we actually calculate the slope to find the equation of a tangent line, we should verify that 5/3 2 root 2 is in fact a point on the ellipse, that this point satisfies the equation. So we substitute in and we have 5/3 squared over 25 plus 2 root 2 squared over 9. 5/3 squared is 25 over 9. And 2 root 2 squared, well, 2 squared is 4, root 2 squared is 2, and 4 times 2 is 8. Right? 25 over 9 divided by 25, the 25s cancel each other out. You're left with 1/9 plus 8/9, which is in fact 1. So we know we have a point on the ellipse, which means that we should be able to find the equation of the line tangent to the ellipse at that point. And we will do so using implicit differentiation. So let's grab this equation. Since I'm out of room on the screen, just slide down a little bit, put that back on the screen, and differentiate implicitly, taking the derivative with respect to x of x squared over 25 plus y squared over 9. That will be equal to the derivative with respect to x of 1. Differentiating x squared, the derivative of x squared is 2x. So we have 2x over 25. The derivative of y squared is 2y. But again, remember, we're taking the derivative with respect to x, not with respect to y. So we have to assume that y is a function of x. And using the chain rule, we get 2y times the derivative of y, which we write as y prime. So 2y, y prime over 9. And then on the right-hand side, the derivative of 1 is 0. Rearranging this equation, we can solve for y prime. And we get that y prime is negative 9x over 25y. Right. Now we have a formula for y prime. As we saw previously, the same thing happens here. Y is not really a function of x. So to find the slope of a tangent line at a particular point, we do need to know an x value and a y value to plug in. But we have those here. We have that we are looking for the equation of the line tangent at 5/3 to root 2. So plugging those into the derivative, we get that y prime is negative 9 times 5/3 over 25 times 2 root 2. Right? Negative 9 times 5/3 is negative 15. 25 times 2 is 50. So y prime is negative 15 over 50 square roots of 2. Divide numerator and denominator by 5 gives me negative 3 over 10 root 2. And then multiplying top and bottom by square root of 2 to rationalize, we get y is negative 3 root 2 over 20. Sorry, y prime is negative 3 root 2 over 20. And again, remember that the first interpretation we had for derivative was the slope of a tangent line. So now we know the slope, we know the point, and we can finish this problem off using the point slope formula to get that y minus 2 root 2 is equal to negative 3 root 2 over 20 times x minus 5/3, and do a little bit of rearranging here. Y minus 2 root 2 is negative 3 root 2 over 20x minus, I guess that'll be plus, minus times minus. We've got a 3 in the numerator and the 3 in the denominator that'll cancel out. We've got a 5 in the numerator, which will reduce with the 20 in the denominator. So we end up with root 2 over 4. Then add 2 root 2. And combine some like terms. Right? 2 root 2 is 8 root 2 over 4 plus root 2 over 4 will give me 9 root 2 over 4. Y is negative 3 root 2 over 20 times x plus 9 root 2. That's not a 2. That's a 2 over 4. And with that, we found the equation of a line tangent to an ellipse at a particular point. Here's a similar problem for you to take a look at. X squared over 16 minus y squared over 9 is equal to 1. This particular curve is a shape called a hyperbola. If you're not familiar with hyperbolas, I encourage you to use Desmos or similar software to sketch out the graph of the hyperbola to see what it's going to look like. And I would like you to find the equation of the line tangent to this hyperbola at the point 2 square root of 5, 3/2. Take a few minutes, see what you can do with this problem, and I'll see you in the next video.